Okay, welcome to the third episode for the meetup of Silicon Valley Quantum Computing Group. Today we have Grant with us and we'll go through my slides and take it from there. So about me, I'm the host for this meetup. I am also working as a director for innovation at Kaiser Permanente. It's a healthcare organization in California predominantly, but we have some offices across the US. My work focuses on digital twin, machine learning, long-term forecasting, as well as some data science stuff. Prior to this, I was the head of ad products at a couple of startups, and then I worked as a consultant in a MIT-based consulting company, Sapient. I have founded a company called Biointegrated Solutions back in 2004-ish, and since then I've been working here and there. I'm also the author of the book Medical Image Processing by Deep Learning. So somebody last time asked me the link and details of the book, so that's the book here. That's why. Today, to help us, we will, prior to I move there, disclaimer, all thoughts are mine and not that of Kaiser Permanente, and they're not responsible for this content. Today, to help me, we will be having a volunteer, Divya. She's a student from Sandermont Middle School. She is a vivid reader and her favorite programming language is Python. So welcome, Divya. She's very interested in quantum computing and reading about it. Today's talk will be on quantum computing by Grant. Grant works at AWS, and then followed by that will be a small fireside chat with me, some questions, and then we'll open up for a Q&A session. Session overview, we talk about classical versus quantum algorithms. We'll talk about the current state of quantum computing. We'll talk about the overview of quantum technologies and some case studies from algorithms in finance. This was also a request that came from one of our participants last time. So I thought this it's good to make that connection and see this as well. Our speaker, Dr. Grant Sultan, is a quantum information scientist with research in quantum error correction, quantum algorithms, and applications of near-term quantum computers to machine learning, optimization, and even quantum gravity. He's a senior researcher at Amazon Quantum Solutions Lab and at the Institute of Quantum Information and Matter. Prior to Amazon, Grant was a postdoctoral fellow at Caltech and a visiting postdoc at Stanford. He holds a PhD in physics from Stanford and master's degrees from Stanford and McGill universities. So welcome, Grant. Really, really excited and happy to have you with us. Before I hand it over to you, I will admit a few people and stop sharing. All yours, Grant. Go for it.
Let me bring up the slides. Thank you for the introduction. Appreciate that. It's really nice to see. Let me know when everything's good to go on your end.
I think we're good to go.
Okay, then let's jump in. So yeah, hi everybody. Nice to meet you all, and thanks for joining this morning. I think it's great to see all of you here on Saturday morning. So yeah, my name is Grant Sultan. We'll be going through some use cases that we've seen here at AWS with some of our customers, and as well starting a little bit earlier by going through some basics with quantum algorithms and quantum circuits. And so this, for the expert, is going to be a little bit low, but just being mindful that we have a bit of a varied audience here, and I thought it might be helpful just at the stage and do a little bit of pedagogy first. So if you're familiar with this, then apologies, but if not, then hopefully you grab something. I think it's also, maybe I'll also just say a disclaimer right up front, right? Feel free to jump in with questions throughout the talk. I'm happy to, you don't have to hold them for the end. If there's something that would help with clarification right away, feel free to jump in. Always happy when it's conversational. So let's look at a little bit of a difference between quantum and classical algorithms. So let's say I've got some input data, x1 to xn, and my goal is to find one of them such that when I put it through some function f, I get a desired marked outcome. Like maybe x4 evaluates through the function f, so that f of x4 is my desired thing. Maybe I'm searching for something in a database, or could be that I'm looking for some sort of minimum or optimum. But one way or the other, I need to evaluate all of these inputs in some, let's say, complicated to implement function f. Classically, the way we could do this is, we take our input data, we try x1, we put it through our computer, our classical computer, it evaluates the function, we get out f of x1. Is that the right answer? Turns out no. Maybe I'm looking for one of the inputs that evaluates the number 5, and this one comes out to 3. All right, so let's try the next one. Start with x2, we put it through our function f, comes out to f of x2, still not the right answer. We do this for all of the values, or until we find the right answer, and in the worst case, we might need to evaluate all of them, all n of those input values to find the one that we care about. And just a note here, if it looks like I'm saying you have to do these things in serial, you have to do, but this problem looks like it can be very nicely parallelized. That's true, but it's not using the metric here that I'm using to decide how difficult it was to solve this problem is the number of times that I call the function f. So while I could have run everything in parallel, and that would give me some time speed up, nevertheless, I would actually, in that case, have to try the function all n times. And so that actually is sort of worse, whereas in serial, maybe I get lucky and the input value that I care about is one of the first few that I try. But importantly here, right, with the classical computer, the way this looks in this sort of trivial setup cartoon problem that I've constructed is that we have to try the function maybe n times overall. Now, what does this sort of look like in the quantum case? Well, if I have some clever way of taking my input data and representing each of those as a quantum state in my quantum computer, then I can do something cool, and I can create a superposition. Let's say it's a uniform superposition over all of those input values. Now, suppose also that I have a clever way of implementing that function f on the quantum computer so that these quantum states that I've constructed are evaluated when I run it through the quantum computer. They are also, the output state is a quantum state representing f of x. So in that case, I run this large superposition state, which is one state, not n different ones, but it's one quantum state through the quantum computer. And after one use of the quantum computer, one use of the function f, I end up with an output state, which is now a superposition of all of the possible outputs. And so, when you read like popular articles on quantum computing, that's often where they stop. They say, now we've managed to try all of the inputs in the problem at the same time, and therefore we've got some massive performance improvement. That's not the whole story, right? It's true that we've set up a superposition of all the data, and this is different from running things in parallel, right? The difference between parallelization and superposition. But now I've used the quantum computer only one time to evaluate the function f, and I've got an output that is all the answers in superposition. But we're not done yet, because we need to know what the answer is. So at the end of the quantum algorithm, we have to measure that state. And if this output state is a uniform superposition of all the possible function values, then when we measure, we get one of those answers at random. So let's say, like we were saying earlier, let's say the input value 4 is the one that we care about. That's the one that evaluates the value we want. Well, in this output state, when I measure, I could get any one of those states as my answer. And when I measure, it collapses the wave function to one of those outputs. And it sort of does so arbitrarily. So the whole enterprise of designing quantum algorithm, the important thing is that you need to change the final output state so that you're much more likely to measure the outcome that you want, right? The whole point of the quantum algorithm is to engineer the process of running it through the quantum computer, that the amplitude, as we would say, the likelihood of measuring all of the incorrect answers is suppressed, and the amplitude, the likelihood of measuring the correct answer is increased, such that when you do this multiple times, then with high probability, you get the right answer, and you can build up statistics and be confident that indeed I found the right thing. And coming up with an algorithm that lets you do that sort of adjusts the weights of these different outputs, that's the hard part of designing a quantum algorithm. That's where we have to think pretty carefully. Generally speaking, this ends up using that function. You end up having to use the quantum computer multiple times, and as well, you need to build up statistics. You have to measure it several times, and so you have to use it more than just one. But nevertheless, we find that in some in some cases, in many cases, we find that we can get away with using the function or the quantum computer fewer times than we could have classically. And in great cases, we find that we can do it exponentially faster. So what does it look like when you try to build up this quantum algorithm? Like what do we see here, right? So what we're generally in the paradigm of universal quantum computation, we're building up quantum circuits. And so the way to understand it is sort of as an analog to really gritty details of classical logic, where you can think of constructing logic at the level of doing Boolean, like this kind of Boolean algebra. You can create a logic circuit built up of and not, and XOR and NOR and things like that. In the quantum case, instead of having sort of inputs that's just classical bits, now our inputs are these quantum states, qubits, and instead of interacting them with things like and not, etc., we interact them with other things that we call quantum gates. And for mathematicians out there, right, you have some large input vector. You can think of it like a vector, and then the gates are transformations on those vectors, which is just sort of like updating the state by doing matrix vector multiplication. And at the end, instead of having some classical logical function evaluated, we end up with a quantum state that is ideally something that is useful. And we've managed to process the quantum information such that we've done, let's say, a calculation that's interesting to us. Now, when we look at these quantum circuits, there are a couple of ways that we try to decide how complicated they are. There are a few sort of metrics that we use. So one of them is how many qubits do we need in order to run? That's one, and it's usually the one that people tend to talk about most, the number of qubits, because we're currently in that stage where we're trying to build up larger and larger devices, and so qubit count is important. But also the length of the circuit, how many operations we need to run in order for this process to end up at a quantum state that we care about. And we call that the depth. And oftentimes when we're talking about the program depth, which is the number of gates that we have to implement, not all gates are actually hard to run on a quantum computer. There's sort of a whole set of gates which we could do pretty efficiently, or actually we could simulate them very efficiently classically. And there's a subset of gates that are really, really complicated. They're really hard, and they're the sort of the things that give quantum computers their underlying inherent power. And so we often, when we're talking about depth, we count the number of those hard to implement quantum gates. So let's sort of see where we are as a field. Now, this is a cartoon. It's a cartoon picture. It's not really to scale, and it's also just meant to illustrate some points. Not everything in here is the disclaimer. Not everything in here is truly state of the art, and of course there are exceptions to all the rules. But nevertheless, this is a cartoon that I borrowed from some of my colleagues in work that I'll talk about later. Yeah, and on the vertical axis here, we've got the program depth. That was the number. Hopefully you can see my mouse, but if not, that was sort of like the length. That was the number of gates in the circuit that we care about, and in particular the number of difficult to implement gates. Later on, they'll be called T gates. That's just sort of some terminology that we're using here, but that's nevertheless sort of the number of gates in an algorithm that we need to run. And on the horizontal axis, we've got the number of qubits. So that's sort of the width of this circuit, not the depth. So pretty clearly in the middle, we've got this sort of dashed line here. So that's representing the high performance computing horizon. Again, cartoon. It's not a hard and fast rule, but roughly speaking, very roughly speaking, we can simulate circuits that have less than 50-ish, 53 qubits pretty efficiently. Or sorry, we can simulate those using classical computers. And the larger the problem size, maybe the more powerful the computer needs to get. But nevertheless, smaller than that, we can, if it's like a few qubits, we can run it on a laptop. If it's tens of qubits to like 50-ish qubits, maybe we need large clusters, or maybe at the very edge we need supercomputers. But nevertheless, we can simulate all of that behavior classically without needing a quantum computer. And just to show you why it's actually sort of a small number of qubits, right? You might have thought we'd need many more, but every time you add a qubit, the available space of state double. And so at 53 qubits, that's 10 quadrillion. That's like 10 quadrillion numbers that we need to keep track of. You can hear me. My power just went out. Could chime in? Let me know if you can hear me.
Yeah, we can hear you, right?
We can hear you.
Okay, doke.
Yep.
Yeah, I'm not sure what'll happen when the power comes back. So I guess you're over
Okay.
here now. And the slides look okay?
Yes, slides look okay.
Okay. So the available space doubles with each new qubit, and the size of the matrices that you need to operate on using when you have 10 quadrillion, or sorry, 53 qubits is like 10 quadrillion by 10 quadrillion. So just think about the amount of space that you need to that you would need in order to store those matrices. It starts to get it blows up exponentially. So we can't really do anything beyond that size without running out of memory. And then on the bottom, we can also we can simulate we can simulate many qubits, but very, very small circuits, right? It's not hard to implement these. So in terms of hardware, where we are right now, we've had a few, slide's not advancing, sorry. My slides not quite advancing as they should have. Well, all right, so let's jump ahead here. So in terms of hardware, available quantum hardware that we've got today sort of fill up this space of the graph, right? We had many demonstrations of early quantum devices that had a small number of qubits and long lifetimes, so they could run very long programs. And then we started to creep towards larger and larger qubit count, for which it gets harder and harder to make big circuits. And only very recently have there been a few examples of quantum devices that have crept into the space that we're calling the quantum regime on the right here. That's where we've got a few, a quantum device has started to have more qubits than we could really simulate, and it pushed up the number of gates in a demonstration beyond what starts to be feasible to simulate classically. And some of this has been disputed, and some of this we could just sort of, with much more clever techniques, we could start to push that up. But really, if you really just start to add a handful more qubits, then we are encroaching into this quantum regime. Importantly, like these are the so-called quantum supremacy demonstrations, and these are sort of highly engineered circuits or programs that people have constructed that are for which the quantum computer is explicitly very good, and the classical computer is not so good. But the current challenge is to try to find something that's in this regime where the quantum computer is actually solving a problem that we care about, the answer, more than just sort of doing the science, but actually let it commercially relevant. That would be some sort of quantum advantage. We're not quite there yet today. For comparison, up here in sort of the very top left corner are some of the well-known algorithms you may have heard of. Shor's algorithm, Grover's algorithm. They require lots of qubits and long programs, where has sort of taken up some of this lower part of the graph originally. And as I was saying, right, we have some demonstrations that are here, just starting to creep into this quantum regime. They are pushing the boundaries of what we were able to, of what we can simulate classically. In some cases, they're sort of stepping beyond that, so it would take too long, or it's not feasible or it's intractable to try to solve these things classically. And the well-known algorithms on the very top right. Hopefully that was clear. Sorry for the technical challenges there. Maybe I'll pause in case something wasn't clear, just because the slides weren't available. If somebody wants to jump in, I'll pause here for a second.
I think we're good. We made it.
Okay. And you do see the slides advancing, yes?
Yes.
Good. Okay. So let's jump into what we're doing here at AWS. So we have many efforts happening in AWS in terms of quantum technologies. I've organized them here, just sort of showing 4 of the overarching efforts. There are other groups that aren't included on the list, but nevertheless, it's just to give you a flavor of what's happening. Roughly speaking, we've got these 4 main pillars. There's Amazon Braket, which is the AWS cloud service for quantum computing. There's an SDK. There's available quantum hardware through third-party vendors. Something that you can just jump into the console and spin up and start using today. I'll go through that in a sec.
We've got the AWS Center for Quantum Computing. That's a research institute in collaboration with Caltech. There's a AWS Center for Quantum Networking, similar sort of idea. It's an industry-based research group. They are working towards quantum networking, quantum communications, things that you'd need for something like a quantum internet. That's they're based out of Boston in collaboration with Harvard. And then there's the Amazon Quantum Solutions Lab, which is a customer-facing research group, kind of like quantum consulting, but it's working with customers to come up with solutions to problems using to come up with aptly named quantum solutions to problems, but not just quantum, sort of anything that can really help move the needle on the customer's end. So let's go through these, starting with Amazon Braket. This is sort of the architecture slide for Amazon Braket. As a user, for the user experience would be that you can start to you can grab the open source SDK. You can start coding this up in whatever, however you like, on your favorite IDE, or you can use the hosted Jupyter notebook through AWS. But once you've sort of built up some quantum circuits that we were just seeing, and have a demo that or something that you'd like to execute, you can run this in the AWS cloud on managed simulators. And we've got 3 of these, and I'll go through these in a second. And when you're ready to run it on real hardware, you sort of change 1 or 2 lines of code, and it goes out, and actually you can run it on real hard quantum devices today through the cloud. And this is all part of the AWS cloud, such that it inherits all the security and all of the integration with other services that you may be used to, right? The results are stored in Amazon S3, and you can import, you can do key management with some of the other services. You can use Amazon CloudWatch for sort of plotting results as they come along, and setting up notifications. It's very well integrated in the public cloud, and the security aspects are taken care of by AWS. So let's see what available devices we got. Right now on AWS, there are ion trap devices from IonQ. There are superconducting quantum circuits from Oxford and from Rigetti. There are neutral atom devices from QEra. These are using the sort of Rydberg state of neutral atoms as opposed to the ions in IonQ. They're photonic devices from Xanadu. And you can see that this list will change over time. It'll grow, it'll shrink. We'll be adding new things, so you can expect to see more offerings coming online, of course. In terms of simulators, there are 3 main ones that are in terms of the that are available as managed simulators. There's SV1, which is a state vector simulator. This is sort of that general purpose, just doing wave function updates with wave functions and unitary gates. That handles up to 34 qubits. And there's a local version of the state vector simulator that can't handle, it's limited by the available hardware that you're running it on, but the managed simulator really takes care of all of the AWS infrastructure that you need behind the scenes, so you don't have to worry about that. Relatedly, there's another one called DM1. This is the density matrix simulator. So this is, if you're an expert, density matrices, as you know, are a way of simulating, let's say, more general quantum operations than you can do with just state vectors. You can include things like noise. So you can do a noisy simulation of a quantum circuit. You can start to create a custom noise model and see what the results would look like when you're taking into account noise that you would see on a real device. Or actually, you can simulate even more general things. Really, for the experts here, you can construct arbitrary Krauss operators and have a Krauss representation to simulate this. This handles 17 qubits, just because you're sort of keeping track of larger and larger things at each time. And then so there's also a local version of this, sort of as part of the local simulator. And then as well, there's a tensor network simulator. This is something that's pretty cool. This is for those who maybe aren't familiar, tensor networks are a graphical calculus for it's a pretty general graphical calculus for sort of updating states. The way this works is that you sort of take operators and you chain them together, and when you contract them and contract, you're really like saying I do a dot product between different indices in different ways. You can more efficiently go from some large expression to the final answer, and it turns out it's possible to embed quantum circuits, and pretty naturally to embed a quantum circuit in this kind of language. So you can simulate larger and larger systems using a tensor network simulator. Currently on AWS, you can do up to 50 qubits. You see that's quite a bit larger, and that's sort of coming up towards that HPC horizon. Turns out you can actually go larger. You can go quite a lot larger with tensor network simulators, but only in certain cases, right? This simulator is designed for being very high performance when the structure that you are of the circuit that you're trying to, or sorry, when the circuit that you're trying to simulate has a lot of structure. So for an arbitrary, highly connected circuit where entanglement builds up very quickly, that's not going to that's the sort of thing that will be harder to simulate on a tensor network simulator. Whereas if you've got lots of structure, short range interactions, then actually these things are pretty, these tensor network methods are pretty powerful. All right. So let's move on, right? So next in the list was the AWS Center for Quantum Computing. And I mentioned this is a research, sort of an industry-based, AWS-based research group. It's in collaboration with Caltech. And so you can see here, this is the office building on campus at Caltech in Pasadena, California. And this is a group of folks who they have a focus on building up, doing the fundamental research required to advance this industry, right? So that includes hardware research, like designing qubits, coming up with new architectures, testing and measuring hardware as they develop it. And then as well, theory research, which includes the underlying theory that you need to build to make this a reality, like doing quantum error correction to reach fault tolerance, coming up with new quantum algorithms and finding applications of these devices. And as well, in building new hardware, there's a lot of theory that needs the support. And so there's a nice symbiotic relationship between those two. And this group is on campus at Caltech and nicely integrated with the university. There's a lot of overlap there.
Mm-hmm.
All right, let's move on. Oh, I see there's some annotations. Maybe Tepos, can you clear those annotations?
Let's see if
so I'll keep going in the meantime anyway. So there's also the AWS Center for Quantum Networking. They're based out of Boston. They're a bit newer, so I don't have some fancy photos of hardware and of facilities. So here I've got sort of the tweet from the CEO pointing out that there's a new collaboration as well. Some press releases from Harvard showing that there is in fact a nice collaboration between those two. This is a group that's focusing on quantum networking and quantum secure communication channels using entanglement to I think I can hear this. Using entanglement to set up the secure quantum communication from one party to the next, and as well using quantum systems to distribute keys so that it's impossible for an eavesdropper to sort of break into your communications. And finally, we've got this Amazon Quantum Solutions Lab. This is a group of research scientists, data scientists, applied scientists, pretty diverse mix of folks who have background in several different things. We've got people that almost everybody has some background in quantum computing. Many people, specialized in quantum computing. Others spend a lot of time thinking about machine learning. Others come in with software development and high performance computing backgrounds, but sort of everybody's at least across two of the three, many across all three of them. And these are folks that are just keen on doing high impact projects with customers, right? So in this case, the customer can really sort of be anybody that comes to us with a hard problem that's fun to solve. Could be major enterprise, could be small startups, it could be universities, right? Pretty open to talking with everybody about cool projects. The idea here is that the Quantum Solutions Lab is focused on finding a novel solution to a customer problem, whatever that may be, ideally using a quantum solution. But in cases where a customer comes in and really they've heard about quantum computing and think maybe that can help, but actually what they really need is something else that they can run today. We have other expertise that lets the group build up a solution that is maybe different from the way they've been solving problems right now. Oftentimes informed by methods we use in physics. Maybe it makes use of machine learning and HPC, but it's not really quantum, doesn't have a quantum component in terms of running on a quantum device. And that is also something that is within the wheelhouse of this group. But generally speaking, what we tried to do is give the customer a way of solving the problem in the future that makes use of quantum computers and is a worthwhile, valuable proof of concept today that lets them upskill and learn. And on the flip side, give them as well another solution that they could use today to find some real value and then transition to the quantum one as the hardware matures. And I'll show an example of this in a few slides. So what I'd like to do now is just sort of cover two case studies. The first one I'll sort of lightning overview, just to sort of give a flavor of what I was talking about on a second ago. And then after I've done that, we'll go into a deep dive into a project that finished recently. So starting with options pricing, right? So options pricing, for those who don't know, an option is a financial instrument that a person can buy that lets them, in some sense, place bets on underlying stocks and assets in a different way than you could if you're just buying the stock itself and deciding when to hold or to sell. It's a contract that gives the holder the right to buy or sell, depending on the type of contract, to buy or sell some underlying asset within some predetermined window. Importantly, at a fixed predetermined price, right? So if you think a stock is going to go up or down, you can, of course, you can always buy or sell the stock if you already have some. But you can also buy a contract that gives you the right to say buy it in the future at a predetermined price that may be lower than what you anticipate. Now the question is, if you're a bank that's offering this to your customers, how do you price it? How much do you charge for that contract? That's the problem of options pricing. And generally, the way this is done is by running large Monte Carlo simulations, where you sort of simulate the evolution according to some model that you've got. Maybe it's proprietary, but you've got some model for how you anticipate things will progress. You run a large number of simulations, and at the very end, you say, okay, the underlying stock is likely to be, according to my guesses, my estimation, this price, and therefore the contract I can back out, I think I should charge this much. Turns out that actually that's a pretty hard thing to do classically. In that it's one of the use cases that takes up a large fraction of compute power for financial institutions, right? You just have to run a large number of simulations, and the more of these you want to run, the more simulations you have to do. And even more than just that, as you start to make the contracts a little bit more complicated and have them involve more than one underlying stock, but have a multi-asset option, then the problem gets to be pretty high dimensional, right? Like you have to run a simulation in a high dimensional space, and it converges really slowly. And so there's a large spend on doing this. So with some, we had some customers ask us about this a few years ago. There was a quantum algorithm proposed for doing options pricing on a quantum computer. It makes use of something called quantum amplitude estimation at the core. Really, what's happening here is it's finding a way to do the sampling that you would do with Monte Carlo quadratically faster. So you get a square root speed up in that process. But this again is a proof of concept, right? We can't actually run these things without a real large-scale, fully fledged, fault-tolerant universal quantum computer, which we don't have today. So we managed to do a proof of concept for that customer running on Amazon Braket. But at the same time, some other customers, they're not, and that customer is interested in learning about quantum computing or evaluating this emerging tech, but they were not actually thinking of this as a way to start to do these today. But with some other customers, they're interested in understanding how quantum computing would work and seeing if we can find ways of leveraging those ideas today. And so there was some other innovation that came out of that group, the Quantum Solutions Lab, for which the solutions that actually able to run on available classical hardware today. There's no quantum computers running in it, but the solution was developed by thinking carefully about some of those tools that people do use for simulating quantum systems efficiently. And in particular, it's using those tensor networks that I was mentioning a minute ago. And it was able to find a large speed up in particular in those multi-asset classes. This is all classical, informed by thinking about quantum computing and physics. And this was giving some value to those customers right now. So tying back to what I was saying a second ago, this means that, for a customer that comes in and says, we'd like to understand options pricing long-term, how would a quantum computer help us? And also, can you do something right now? The answer is yes, right? We give them something that they could run today on available classical hardware, but is still using the language of these quantum computers. And so it's pretty natural to take that simulation using a tensor network and update this to run on a quantum computer down the road, and then also giving them something that would work as a proof of concept today. All right, so that was just to sort of help understand, roughly speaking, what I was trying to say with these multiple work streams and how this interdisciplinary group of scientists can find cool solutions. So if you're out there and you're listening and you think, oh, we've got the problem we'd like to solve, maybe we're interested in evaluating a quantum solution, maybe you're actually just thinking about you've got a problem that you'd like to find some performance improvements, as an optimization problem, for example, and it's not actually it's one that you're running up against the wall, and you think some new insight or coming at this problem from a different angle might actually give you some value, then yeah, please reach out. This group can see if there's something cool we could do together. All right, so the second and last case study, this was some work that we did with Goldman Sachs on understanding a quantum approach to portfolio optimization. So there were 2 papers that came out of this collaboration. Listed here, I gave the archive numbers, and I think this was a nice one, because Goldman Sachs is a they're deeply interested in quantum computing approaches and not necessarily trying to get a value out of it right now. These are researchers who, all of whom have PhDs in quantum computing or something adjacent, some sort of quantum information technology. They understand the current state of the art, and they're really trying to evaluate the usefulness of this technology for the firm going forward, not looking to get something out of it right now. They really understand the state of the art. So together with them, we had to try to come up with something cool to work on. So the first thing that we had to do was figure out exactly what it is we wanted to study. And that meant sort of going through a laundry list of possible use cases, things like portfolio optimization, options pricing, many others that I'm not mentioning here, and a laundry list of ways of solving these kinds of problems using quantum devices. That includes that included several quantum algorithms that have been proposed that give you some promised quantum speed up. We also looked into using a different type of quantum device that does not use those circuits. They're talking about these quantum annealing devices. Sort of looked at all of them together in a holistic sense and tried to find where we thought there would be the most promise towards coming up with a use case that we would solve with an algorithm. And with all of that at our, once we'd gone through all of that, we sat down and we said, all right, okay, we think we've got an idea. So we landed on studying portfolio optimization using a quantum algorithm that had been proposed for doing portfolio optimization that at its core uses something called second order cone programming. It's just for the experts. There was a quantum algorithm for doing that, which had been shown to give some quantum speed up for doing portfolio optimization. And so we said, all right, let's see how hard this is to actually implement, right? Like, the theory is done. Let's go through this end to end and count these quantum resources that we would need to solve it. And the outcome was, these 2 papers, one on a resource estimation for doing portfolio optimization using these quantum zero point methods, which I'll go through now. And another was just doing careful accounting of these resources for actually loading data into the quantum computer, which I'll also talk about. Okay, so let's go through what this actually looks like. Just a quick recap in case somebody's not familiar, but this is the standard approach to portfolio optimization. It's called modern portfolio theory, or the Markowitz model, named after Harry Markowitz. So generally speaking, let's say I'm trying to invest I've got some money. I got $1,000 burning a hole in my pocket. I want to invest it into some number of stocks. Let's say I want to pick some of the S&P 500. I want to pick a few of those, and I want to put my $1,000 into those. How then do I allocate my $1,000 into some number of the 500, those 500 stocks? Well, maybe what I want to do is I just want to find the largest possible return that I can get. I just want to make as much money as possible, and so I want to maximize my returns. Or maybe I'm trying to actually do this so that I'm saving for retirement. I want to make a little bit of money, some fixed amount, but my goal is to do so with the smallest risk to me losing the rest. And so I want to minimize my risk. Or maybe I'm trying to do some sort of like hybrid model where I want to maximize my returns and minimize my risk. And this Markowitz model encapsulates all of this and much more. It's quite a rich model. Here, W, this vector W, this is a vector of weights. So this is how much money, W1 is how much money I put into stock 1, W2 is how much I put into stock 2, and so on and so forth. So this is the amount of my money that I'm allocating to each stock. And I am trying to find a distribution of those W's that either maximizes my the amount of money I make, maximizing the returns, this is a vector of return, or minimizing my risk. And this is sigma here, this is representing some covariance matrix. So we don't have to go into the details. And this seems like a fairly simple quadratic program, right? If you're used to solving problems, it seems like a simple thing, but the model actually gets quite in depth when you include constraints. So maybe I want to make sure that in my portfolio, I don't want to include any of those short trades, right? Like including options. Maybe the options were on the table, and I don't want to include those things that we were talking about a second ago. I want to only have long trades. Maybe I want to make sure that one particular stock has at least some fraction of my money, but not more than a certain amount, that particular stock. I want to make sure that I've invested in it because I really believe. So I have some investment band. Or actually, maybe I want to make sure that of the 500, I have at least 20 and no more than 25 stocks in the portfolio. So I have some cardinality constraints on the portfolio I'm trying to choose, or I can include transaction costs, which is some term that would be added based on, usually it's a charge that is levied upon you proportional to the amount that you traded. So there's a whole, there's a ton of these different constraints and other things that you can add to the model. And they start to make this problem a little complex, such that it gets difficult to solve, like computationally difficult to solve, especially as the number of possible assets grows. And so generally, there's one way of solving these kind of constrained optimization problems that make use of inferior point method. This is all classical, right? An inferior point method, looking at the cartoon I've drawn here, the way you solve this problem is by saying, okay, I pick some solution to that problem. I find one vector W that I find one portfolio that satisfies all of the constraints. So it's feasible in that sense. If a solution is feasible if it's satisfying all the constraints in the problem. So find one of them. It doesn't have to be a good one. And then what I do is I sort of iteratively update the portfolio along some very important trajectory until eventually I land at this optimal solution. And there's some careful math that goes on in the background here, but you can prove that actually if you move along this curve in a very carefully defined way, that you're guaranteed to land at converge on some optimal solution, so long as you stay within a neighborhood of this curve. This is called the, I've just drawn a blank here. Shoot. This is called the central path, right? So as long as you can follow along this curve and stay close to it, it's written right here. As long as you can stay close to the central path, you converge on the optimal solution. Now, how do you know which direction to go? Somewhere in this algorithm, you have to solve a system of linear equations, right? You think of it like I take some derivative and I'm just sort of moving like along this path in a linear way. There's a system of linear equations that I need to solve. And at each point, this ends up being a bit of a bottleneck, solving the system of linear equations. So you can find a quantum interior point method if you upgrade that system of linear equations to a quantum linear system solver. And generally, this is roughly speaking how quantum interior point methods work. So we were looking at this proposed algorithm for doing portfolio optimization that makes use of one of these quantum interior point methods. In particular, it's a quantum interior point method for solving a second order cone program. That this acronym here is just it's a smaller class of problems, but one where the portfolio optimization fits, and so it's a little bit easier than a general constraint optimization problem, but nevertheless you still use these quantum interior point methods. Let's see what goes into doing this. Right, there are several things you need to do. First, I hand you a bunch of the historical stock data, right? I tell you that I give you, these are the historical average returns that you've gotten, and here's the covariance matrix telling you how all the stocks seem to depend on one another. From this, come up with this, come up with the portfolio that you're trying to optimize. In order to do this in the quantum computer, in order to come up with that linear system that we need to solve, linear system AX equals B, that matrix A and the vector B, that depends on this historical stock data. It depends on the stock prices. It depends on the covariance matrix. So I need to be able to bring that data into the quantum computer so that I can solve it. If you think back to the beginning of the talk, I was showing how a quantum algorithm works. We created a superposition of all that input data. I said, you need a clever way of storing that data in the computer. And then we use the computer to implement that function F. And I said, you need a clever way of applying that function F in a quantum way. And so how do you do this in this portfolio optimization case? You need to be able to bring the data into the computer and represent things such that you can repeatedly use it in a coherent way. And an approach to doing this is called block encoding, and it makes use of something called quantum random access memory, just sort of a way of storing data. And so that was sort of an enterprise, right? That was a way of bringing data into computers that had been proposed. We studied this for the sake of really getting to the details of how hard it is to do. Once you brought the data into the computer and you've got your matrix A and your vector B and you want to solve AX equals B, now you need to use some sort of linear system solver. And there are many algorithms that have been proposed to do this, going back many years now. But since the inception of the idea, there've been several updates. Was there a question?
Yes.
There was or was not? I'm sorry. I didn't hear.
No, there isn't any question.
No. Okay, gotcha. So there's been several updates on building these quantum linear system solvers. So in our case, if we're trying to give ourselves a fighting chance for using this quantum algorithm to solve a problem that we care about, maybe we should upgrade to the state of the art. So something that uses the smallest number of resources and the most efficient linear system solver. So we did that. We upgraded to the state of the art linear system solver, and putting that together with this block encoding concept. And then as well, if you remember back to the beginning, I said at the end, you need to be able to measure the quantum state, get your answer, and you have to do this many times to build up statistics to make sure that you trust your answer. So that's the process called, that's something called tomography, where you're just sort of measuring quantum states many times, building up some representation of the underlying state so that you know what the state is. You have to do that as part of this process, and that requires many repetitions. And there are several ways of doing tomography, so we have to think about the best way for this problem and try to bring down those costs. And then as well, in going through this whole end-to-end thing where you're stringing together many bits and pieces, you can find some places to optimize. So you can bring in some performance improvements and get rid of bottlenecks, and also sometimes there are bugs in other analyses, and so you have to just sort of fix those bugs. And so we did that. We sort of did all of it, and that gave us two results. So we'll focus on just the first part here. So just to recap, just to emphasize, we're looking at this block encoding. How do you store quantum data in a quantum computer? That was the first of the two papers from the group. And there are some equations. So let's get rid of equations to make this a little bit easier to digest. So here, the question is, how do I load data into a quantum computer? This is not specific to portfolio optimization. This is just saying, I hand you a matrix A. How do I load that into a quantum computer so that I can use it in a quantum way, using this procedure called block encoding, which is the standard way that people use this in quantum algorithms. And we said, in order to do that, how many qubits do I need, and how many of those computationally expensive gates that I was talking about earlier do we need? So that was what I was saying, right? These computationally expensive gates, called these P gates, or how many of them in total, whether it's if we allow for parallelizations, I just want to know in total. And there are several ways that you can do this. Some of them minimizing the number of P gates if you allow for parallelizations, or minimizing the total number, depending on what you think is more important. But the important thing here is, if I hand you a matrix, let's even look at the small size. If I hand you a 16 by 16 matrix, not very big, easy to write down, 16 by 16 matrix, that uses either like 400 to 1,000 qubits just to load that matrix into the quantum computer. Kind of expensive. And if we start to go to larger problem sizes, even 4,000 by 4,000, that's not hard for a classical computer. But if we start to get up there and it starts to get to more relevant problem sizes, we need sort of either on the small side here, you need like 800 to 1,000 layers, a depth of 800 to 1,000, or if we're looking at the count, minimizing the count, it's still like a million or so, in the orders of millions of these hard to implement gates. So I'll put that into the context in terms of this picture that I showed earlier. Where does that sit? That sort of sits here. We had these two approaches. That's why there are these two lines. And you can see, right, for the small size matrices, they're already sort of squarely inside this quantum regime. And then as we start to increase, they start to use lots of qubits. The scaling here with depth is pretty good. Actually, that's a really good scaling. This log depth is pretty good. It's not increasing on this vertical axis. It's just using lots of qubits, and that's what we were finding. To recap, that was just for the problem of loading the data into the quantum computer. Then we looked at the full portfolio optimization problem, and so here's the answer. Like here's the final answer after this long-winded build-up. Here's the final answer of how hard it was to do. We looked at, for a simple problem of 100 stocks, which is very small, right? That's the kind of thing you can do on a laptop without too much trouble, just using like open source solvers or something. With 100 stocks, and for the experts, a duality gap of 10 to the minus 7. For the non-experts, this is sort of a way of knowing how close you are to the optimal solution. This was a number that was informed by some folks that were doing this daily, and they said, yeah, that seems roughly correct. What we found was that at the very end, after you've done this full interior point method, you need 10 million qubits and like 10 to the 24 layers. The depth was 10 to the 24. These are sort of astronomically large numbers. Let's put that into perspective, right? Let's say that all of the gates that you can run on the quantum device are free. They happen instantaneously, with the exception of these hard to implement T gates. And let's say that all T gates that I can run in parallel can happen at the same exact time, and then I get free parallelization of those T gates. So I'm really only talking about like the number of layers of them. And let's be very optimistic and say that each layer of those T gates takes only 1 nanosecond, which is a gigahertz clock speed, which is that's a very aspirational goal. We're not near there in terms of hardware. So giving ourselves a very being very conservative. With those assumptions, a depth of 10 to the 20, so 10 to the 24 layers of those things would take tens of millions of years, which is clearly infeasible, right? That's not going to work. And in fact, just this QRAM alone, what this means is just doing the stuff I showed in the previous slide of loading the data into the computer had some key depth requirements for the problem size that we care about. It was about 10,000 years. And so by contrast, this problem is pretty trivial on a laptop. So what's that's not that sort of sounds bad. And just to give you some insight into where these numbers, why they're so large, if you're wondering, this is an iterative algorithm. This interior point method, you have to sort of like, you do something, you update, you do something, you update. You have to repeat. So there are, you have to do 10,000 in a for loop, right? Like a classical for loop, there's 10,000 classical iterations. And at each one of those iterations, you needed to measure the state, the underlying state, many times to build up statistics that to a very precise degree what the underlying state is, that thing I was calling tomography. Actually, you need to do it like 1 billion times per iteration. So you end up with these huge numbers. Without it, in a single run, there's where you don't actually, you do these repetitions. Single run has these numbers here. They're still pretty large, actually. Not astronomical necessarily, but still quite large, right? 10 million qubits, still kind of large. And for experts, these are all logical qubits, meaning there's no quantum error correction overhead here. These are all assuming perfect qubits and perfect gates, which makes things a little worse. Where does this sit on the final graph here? This was the current state. It sits up here. It's a large problem depth, and actually it sits up here. It's sort of showing it that trying to get off the screen. It's actually somewhere way over there off the screen. It was like 10 million qubits, and this is 10,000 qubits, so it's a few orders of magnitude off the screen to the right. So that's kind of, that's not so great for this algorithm. Why is it that I think this is not, why am I so excited about this, right? Like, and not just sort of defeated. It's a negative result, to be clear. It is a negative result for this quantum algorithm. It's showing that it's not really feasible to run it for problem sizes that we care about. Once you start taking into account all of the nitty-gritty details, How do you bring the data into the computer? How do you make sure that you've built up your statistics carefully? How did we do this with the most advanced available techniques today, and bring everything up there? When we start to count things, once you've tied them all together, it starts to look like it's pretty expensive. And that is the case, but it was very, very informative, right? First, off the bat, yes, it sort of says that these iterative quantum interior point methods in their current setup will need to be improved in order for them to be feasible. But putting that aside, it kind of pointed out explicitly where we need to focus effort in order to have algorithms of this form, or just where we should put lots of effort into quantum algorithms research in the future, right? We found that even the problem of loading data into a quantum computer, which is something that is kind of crucial and you have to do with many algorithms, that already can be quite expensive. And so maybe we need to focus an effort on building dedicated hardware that is designed for doing this. We have this in our laptops and our regular computers, right? There's RAM and there's long-term storage. And think back to the old days, we had hard drives and RAM, and there were different types of memory for different purposes. Long-term storage versus quick random access. Those are different things that you don't necessarily want the same type of storage. But you remember the old days of coding, you would hit swap and suddenly things grind to a halt. So why not do something similar here, right? Like for storing data and loading into the quantum computer, we sort of we advocate that it's important that we may need different types of hardware that are better designed for these primitives. And then as well, we sort of understood where there are major bottlenecks in the quantum algorithms, and so we pointed out where we need to focus efforts to improve our quantum algorithms. Things like homography aspect, and then other places where there are bottlenecks in these algorithms that we need to focus on. And so this was, I think, it's exciting, right? The other thing too is that we were sort of advocating that it doesn't, it's important to come up with a new quantum algorithm and show that asymptotically in the long-term limit and with ideal computers that there is a promised quantum speedup. But in order for that to be something that's useful and can actually start to compete against a classical computer on problem sizes that are relevant, it's important to go through the exercise of doing this end-to-end analysis to see whether or not once all the dust settles, you're still going to find this quantum speedup. So it's sort of it raises the bar for saying we've found quantum advantage, right? You can't, in order to demonstrate quantum advantage or to even advocate that an approach can lead to quantum advantage, we're sort of suggesting maybe you should also try to do one of these end-to-end analyses to make sure that actually everything is going to work as expected. And you find the details of this work in here. And so with that, I think I'm done. I think that's it. So we can. I'm happy to open up for some questions.
Sure. And I'm gonna pause the recording right now, as you requested, so that we can ask some questions.